This video clip is part of the EPFL introductory course on information computing and communication. It is the fourth in a set of video clips on computer architecture. The von Neumann computer architecture described in the second video clip of this series on architecture is still abstract. So far, it has not been said how it can be implemented with any technology such as transistors. The present video clip and the next one will answer that latest question. Together, these two clips will show how a computer following the von Neumann architecture can be completely implemented with transistors. Such computers can then execute any binary object program as defined in the previous video clip of this series. Combined, such hardware and software can be leveraged to implement any computing device, from actual computers to any other kind of computer-controlled device, such as a tablet, a smartphone, a digital camera, or so many other household and industrial devices. In fact, the von Neumann computer architecture as specified so far is so abstract that it is not even tied to any particular technology. To be clear, binary encoding happens to be a good idea if one thinks about implementing computers with digital transistors. However, even this is not a strict requirement. Other encodings might work just as well for other implementation technologies, although these might not be as compact, as fast, as efficient, and as inexpensive as transistors. In fact, in older days, before transistors, computing machines using binary or even other encodings have been built with only mechanical elements. Later, they were built using electromechanical relays, then electronic tubes, and eventually transistors. Today, many researchers are looking to implement future computers with optical switches that could be yet faster and consume less energy than transistors. Given that today's computers are still built out of transistors, though, let us explain how that is achieved. For a start, digital transistors being electronic devices, they need power. This in turn calls for a convention tying power to binary values. There exists a variety of computers using different power conventions, but to be concrete, many of them operate on a 1.5 volt power. In such computers, a natural convention is to consider the power level of 1.5 volt to represent a binary 1 and the ground power level of 0 volts to represent a binary 0. The interest of using binary coding to implement computers with digital transistors is that such transistors function as switches. Note that whenever one talks about transistors in digital computers, one talks implicitly about digital transistors. Many electronic and electrical devices use analog transistors, which function as amplifiers but not as switches. So the natural question is, what is binary about a switch? What's binary about a switch is that it can be in one of two positions, opened or closed. In the open position, the upper line on this slide, a mechanical switch does not propagate its input to its output. Its output is floating and undefined. In the closed position, the lower line on this slide, the mechanical switch connects its output to its input so that the output equals the input, 1 or 0, 1.5 volts or 0 volts. Digital transistors differ from mechanical switches in the way they're flipped. Strictly mechanical switches must be flipped by some mechanical action, such as a human hand. Digital transistors are more like electromechanical relays in that their flipping can be triggered by an electrical signal. By applying a 1.5 volts, or a 0 volts, to such a transistor, one can cause it to open or to close. Whether a digital transistor is opened or closed by applying a 0 or a 1 to flip it depends on the transistor technology. In modern so-called complementary metal oxide semiconductor technology, abbreviated CMOS, There are two technology families. The negative one, NMOS, on the left side of this slide, and the positive one, PMOS, on the right side of this slide. In either technology, transistors present three connections: their input, their output, and their so-called gate, which controls the flipping of the switch. Graphically speaking, PMOS transistors are distinguished from NMOS transistors simply by an additional small circle on their gate connection. NMOS transistors are such that they close when one applies a logical 1.5 volts, to their gate, and they open when one applies a logical 0 volts. PMOS transistors work just the other way, opening when a 1 is applied to their gate and closing when a 0 is applied. In any case, such transistors today are extremely small, extremely fast, and extremely inexpensive, at between 1/10,000th and 100,000th of a cent in any of the main currencies. Even though a single transistor does not consume that much power, modern computer circuits pack so many billions of transistors into one chip that the power consumption density would reach limits beyond which chips could no longer be cooled. Thus, although transistors keep getting smaller and thus could switch faster, this would require more power, which would melt the chips, so that switching speeds from now on are in fact limited. The next question is how transistors can be assembled into functional circuits, such as arithmetic units. To start, let us build the simplest possible Boolean logic circuit, an inverter implementing the binary function NOT. The picture shows such an inverter built out of just one NMOS and one PMOS transistor with one input A and one output X. Indeed, if one connects the top of the circuit to a power wire, 1.5 volts, and the bottom of the circuit to the ground, 0 volts, the output X will always be the opposite value of the input A, as can be verified on the next slide. The bottom left of this slide shows what happens when one applies a logical 1 to the input A. Getting the input of 1 applied to this gate, the PMOS transistor at the top of the circuit opens up. On the contrary, the NMOS circuit at the bottom of the circuit closes, thus connecting the logical output X to the ground, which is a logical 0. The bottom right of this slide shows that just the opposite happens when one applies a logical 0 to the input A. Getting the input to 0 applied to this gate, it is the NMOS transistor at the bottom of the circuit which opens up, while the PMOS transistor at the top of the circuit closes, thus connecting the output X to the power pole, which is a logical 1. Any such logical circuit can always be described in pure logic terms by its so-called truth table, which specifies which output is yielded for every input. The truth table of this NOT function clearly states that X is always the logic negation of A. The most elementary circuits, such as this NOT, are also often represented graphically by a logic symbol, such as shown here. The logic symbol for a NOT circuit is a triangle, actually the symbol for an electrical amplifier, followed by a small circle indicating the negation. This slide shows the transistor circuit, the truth table, and the graphical representation of another important and frequent circuit, a NAND gate. NAND stands for not AND. In other words, the output of the circuit is a logic negation of ANDing its two inputs A and B. Whereas the straight AND logic function yields an output of 1 if and only if both of its inputs are 1, the NAND logical function, and of course any circuit implementing it, yields a 0 output if and only if both of its inputs are 1. This is exactly what the NAND truth table specifies on this slide. It is also exactly what the transistor implementation yields when one applies logic 1s and 0s to its inputs A and B. For the output to be 0, both of the lower NMOS transistors must be closed to connect the ground to the output, while both of the upper PMOS transistors must be open to avoid short-circuiting the power source. This is indeed the case when A and B are powered to a logic 1. On the contrary, as soon as A and B, or both, are grounded to 0, one or both of the lower NMOS transistors opens, thus letting the output float. At the same time, one or both of the upper PMOS transistors closes, thus connecting the output to the power source, meaning a logic 1. Quite naturally, the symbol for a NAND circuit is the same as that for an AND circuit, simply followed by a small circle indicating the negation. This slide shows from left to right the transistor implementations, the graphical symbols, and the truth tables of a couple more popular and frequently encountered circuits, NOR in the upper half of the slide and XOR in the lower part of the slide. The logical OR function yields a 0 output if and only if both of its inputs, A and B, are 0. The NOR function is the negation of that, i.e. it yields an output of logical 1 if and only if both of its inputs, A and B, are 0. This is what the truth table states, and indeed what the transistor implementation yields. The output can be 1 if and only if A and B are both 0, thus connecting the output Y to the power, logical 1, through the upper PMOS transistors which are closed, while the lower NMOS transistors are open. As soon as a logical 1 is applied to either A or B, or both of course, one or both of the upper PMOS transistors opens, thus letting the output Y float, while one or both of the lower NMOS transistors close, thus grounding the output Y to 0. The logical XOR function in the bottom part of the slide yields a 0 output whenever both of its inputs A and B are equal to 0 or to 1. When the two inputs differ, i.e. one of them is 0 and the other is 1, the XOR function yields a 1 output. This is what the truth table states, and indeed what the transistor implementation yields. The output will be 0 every time A and B are equal to 0 or to 1. Because the left part of the circuit implements a NOT A, while the right part of the circuit looks like a NOT circuit, but is fed by A at the top and by NOT A at the bottom. As a result, when A and B are equal, either both NMOS transistors are closed and both PMOS transistors are open, or the other way around. Thus, when A and B are 1, the output is grounded to 0, while when A and B are 0, the output is connected to A, which is 0. On the contrary, when A and B differ, one of the NMOS transistors and the diagonally opposed PMOS transistor will be closed, while the other two transistors will be opened. Thus, the output will be connected to A when A is 1, and it will be connected to not A when A is 0, meaning that this output is going to be 1 in either case. As stated earlier, the truth table of a circuit always completely specifies its function by stating what its outputs should be for any possible inputs. Thus, in the case of a circuit with 2 inputs and 1 output, there are 2 to the power of 2 possible input combinations, and thus 4 possible outputs to be defined. Any binary function, as stated by its own truth table, can be implemented by some transistor circuit combining elementary logic functions in some more or less complex way. On this slide, for instance, the truth table states, and the transistor circuit next to it implements, a binary function of which the output xy is the binary representation of the sum of 3 bits, A, B, and C. In other words, this circuit is nothing else but a 3-bit adder, an extremely important basic building block for many more complex circuits, such as, for instance, a complete arithmetic unit.